So we've covered a lot of the derivatives of polynomial functions, trigonometric functions, and their variants. In this video, we're going to be covering the derivatives of the exponential function and the natural logarithm function. The natural exponential function e to the x has the wonderful property that its derivative is actually itself. So if you wanted to find the rate of change of e to the x at any particular x value, well, you just plug into the function e to the x and you'd get it. For example, if you wanted to find the rate of change of the function at x equal to 1, it would just be e to the 1, e, which also happens to be the function value at that point. But what if we want the derivative of e to the 5x with respect to x? Well, this is just going to be of the form, the derivative with respect to x, of e to some function u of x. So e is raised to a function of x rather than x itself. And this is just going to be the derivative with respect to u of e to the u, which is e to the u, times the derivative of u with respect to x. And in this case, u is 5x, so this would be e to the 5x times 5, or 5e to the 5x. What about the derivative with respect to x of e to the 3x squared? Well, here u equals 3x squared, so this would be the derivative with respect to x of e to the u would be e to the u du dx. So that's just going to be e to the 3x squared times 6x. Or alternatively, you can put the 6x out front. Write it as 6x times e to the 3x squared. But what's the derivative of f of x equals ln of x? Perhaps you remember that ln of x is the inverse of f of x equals ln of x is the inverse of g of x equals e to the x. But before we go over what the derivative of ln of x is, let's briefly review what inverse functions are. We call that f and g are inverse functions of x if and only if they're functions for which for every point xy on f of x there is a point yx on g of x. This is equivalent to saying that the composition f of g of x equals the composition g of f of x, which equals x. Or in other words, both the compositions f compose g and g compose f of x equal x. And this is in turn the same thing as saying that g undoes whatever it is that f does, and vice versa. So f undoes whatever it is that g does. Now I'm going to give you some intuition behind why the three statements that I said were equivalent are actually equivalent. And those statements are for, if you know that both f and g are functions, you can deduce that they're inverse functions if either of these three criteria, any of these three criteria are met, and these three criteria are essentially saying the same thing. So let's say you plug x into the f machine here. So it'll take as an input x and it will spit out ln of x, right? And what is ln of x? It's the power to which you raise e to obtain x. And now you plug in that result, ln of x, as an input into the g machine, which will take whatever you input and raise it to the x and perform an e to the x operation on it. So ln of x is basically asking, well, what power do you raise e to get x? And now we're going to actually be raising e to that power. So you might expect that we'll be getting x out. So first, input x into f, and we get as an output the power to which we raise e to get x. and then we input that power for x into g. So you'd expect that we get x as a result. So you can see here that the composition of f of g of x is clearly x, right? We first perform, or sorry, this is g of f of x. We first perform f, then we perform g on the result of f, and we got out x. So this is the g of f of x case. In other words, you can see that g undid what f did. So f took x and it spat out the power to which we raise e2 to obtain x. And then g raised e to that power to give you back x. So in this case, g undid what f did. Now let's look at it another way. You input an x into f and you get a value for y. And this, but what would be y on f of x, you input as x into g of x, and you'll get a new y. And this will hold true for any x that you input into this sequence of functions here. So if you input x into f of x, you'll get a y for f of x, and you will input that value of y for f of x as an x into g of x, and you'll get another y. So it should be clear that for every x, y on f of x, there's going to be a yx on g of x. But let's say we looked at the reverse process. So we did applied g to x first, and then we applied f to the result. Well, that would be the composition f of g of x. We earlier considered the composition g of f of x, now we're considering f of g of x. So when we plug in x into g, g will take x and raise e to the x power, and will output e of x. And we plug that result into f. Well, f will apply the natural logarithm to e of x, and that will be equivalent to asking, well, what power do we raise e to get e of x? And think about that question again. What power do we raise e to get e of x? Or to get e to the x, sorry. What power do we raise e to get e to the x? Well, we'll clearly raise e to the x power to get e to the x, right? So then we will be, f will spit out x. So in this case, it's clear that f undoes whatever g did. Or in other words, for every xy on g of x, there's going to be a yx on f of x. And to reason through that, think of it like this. You'll input x for g of x. G of x will spit out a value of y. You will use that value of y as an input for x into f, and you'll get a new value of y here. But remember, this new value of y is equivalent to the old x that you inputted into g. And the value of x that you inputted into f is equivalent to the y output from g. So here, for every x y on g of x, there's going to be a yx on f of x. So I've drawn the graphs of f of x equals ln of x and g of x equals e to the x. And you can see here that for every xy on f of x, there is a yx on g of x. So for example, the point 1, 0 on there's a point 1, 0 on f of x, so you'd expect there to be a 0.01 on g of x, and there most certainly is. Likewise, there's a point E1 on f of x equals ln of x. So you'd expect that there's a point 1 e on g of x equals e to the x, and there most certainly is. Finally, there's a point e squared 2 on f of x equals ln of x. So you'd expect for there to be a point 2 e squared on g of x equals e to the x, and there most certainly is. Now, to think about these inverse functions from the composition vantage point, let's say you plug in 1 into f. Well, f is going to output a value of 0, right? And if you plug in that result 0 for x into g, well, g is going to output 1. You started with 1 that you plugged into f, got a result, plugged that result for x into g, and you got back 1. If you do the same thing in reverse, let's say you plug in 1 into g, well, you're going to get an output of e, right? But then you plug in e as an input into f. Well, f is going to output 1. So regardless of which you plug into first, f or g, you will get back, if you perform a composition, you will get back your input value, the value that you inputted into the first function. And the same reasoning that we use to use for the points 1, 0, 0, 1, we can use for the other pairs e1, 1e, and e squared 2, 2e squared respectively. So knowing now what we know about inverse functions, can we use that to come up with an expression for the derivative of ln of x? Well, let's see. An inverse, if f and g are inverse functions, I guess I should say assuming f and g are inverse functions, then we know f of g of x equals x. What would happen if we differentiated both sides of this equation with respect to x? Well, if we differentiated the right side, we just get 1. If we differentiated the left side, we get f prime of g of x times g prime of x. Remember, this just follows from the chain rule. And if we solve for if we solve for g prime of x, we get 1 over f prime of g of x. But how does this help us find the derivative of ln of x? Let's say g of x equals ln of x, since that's the function whose derivative we're interested in finding, and f of x equals e to the x. This tells us that the derivative of ln of x, remember here that's g prime of x, is going to be 1 over the derivative of e to the x evaluated at x equals ln of x. So first we'll compute the derivative of e to the x. Well, that's just e to the x itself, right? But instead of evaluating this expression at x, we want to evaluate it at ln of x. So when we do that, we get 1 over e to the ln of x. Well, what's e to the ln of x? Well, ln of x is just asking to what power do we raise e to get x. And if we raise e to that power, we're going to just get x back, right? So now we finally have an expression for the derivative of ln of x, and it's 1 over x. What if we want the derivative of ln of x squared plus 5? Well, ln of x squared plus 5 is just the composition f of g of x, wherein g of x, the interior function, is x squared plus 5, and f of x, the outer function, is just ln of x. Well, the chain rule tells us that the derivative of f of g of x with respect to x is f prime evaluated at g of x times g prime of x. In this particular case, that would be ln of x, but evaluated, or the derivative of ln of x, but evaluated at x squared plus 5, because that's g of x, right? So 1 over x squared plus 5 times g prime of x. Well, that's going to be the derivative of x squared plus 5 with respect to x. That's 2x. And this is, again, the derivative with respect to x of ln of x squared plus 5 equals this stuff here. That's just going to be 2x over x squared plus 5. But what if instead of asking you for the derivative of ln of x squared plus 5, I'd asked you for the derivative of ln of 3x cubed? Well, ln of 3x cubed is just f of g of x, wherein g of x, the interior function, is 3x cubed, and f of x, the outer function, is ln of x. If we would like to differentiate that function with respect, that composition with respect to x, that'll be f prime of g of x times g prime of x. And remember, this just follows from the chain rule. F prime of g of x is really the derivative of ln of x, but evaluated at g of x. So instead of 1 over x, we'll have 1 over 3x cubed. We'll multiply that by the derivative of this interior function, 3x, the derivative of 3x cubed, which is 9x squared. Make some cancellations, we get 3 over x. But we actually have a problem here. This problem might not be immediately obvious, but notice that 3 over x is defined for all x not equal to 0. So x equals 0 is really the only problematic number here. So you could say it's defined over the interval negative infinity to 0, exclusive of 0, union 0 to positive infinity. I guess I should really say that it's defined for these x values. But where's ln of 3x cubed defined? Well, we know that ln cannot take a 0 or negative argument, because e raised to any power is always going to be positive. Even if you raise e to a negative power, you will get a positive result, right? So we know that this 3x cubed has to be positive. So we could say ln of 3x cubed is defined for 3x cubed greater than 0, strictly greater than 0. But this is equivalent to saying that it's defined for x cubed strictly greater than 0. You divide both sides of this inequality by 3, you'll get x cubed greater than 0. But if you take the cube root of both sides, you'll see that this is strictly defined for x greater than 0. So if x cubed is greater than 0, that necessarily means that x must be greater than 0. So ln of 3x cubed is only defined for positive values of x. So that's this interval here. X is an element of 0 to positive infinity, exclusive of 0. So here we have a situation where the derivative seems to be defined over a wider interval than the original function itself. Is that possible? Can the derivative of a function be defined where the original function itself is not defined? And the answer is that it cannot, because remember, the derivative is the instantaneous rate of change of a function. And we can only think of that instantaneous rate of that function where that original function is defined. So the derivative here in this case is not 3 of x. It's 3 of x over 3 over x. The derivative is not 3 over x. It's 3 over x over the interval for which over the x values for which ln of 3x cubed is defined. So it's 3 over x for x greater than 0. So you really have to be mindful that when you do the algebra and you get a result for the derivative of a function, you have to take into consideration the domain over which that derivative is defined. And it's always going to be an interval equal to or smaller than the interval over which your original function is defined.